Hi everyone and welcome. Today we're going to be talking about stability of equilibria, which turns out to be a very useful tool for studying nonlinear differential equations. Differential equations are really at the core of a lot of different models that we might want to put together, and especially nonlinear ones. But the solutions of these nonlinear equations are really hard to come by. In fact, they're almost impossible to find most of the time. So we need some way of studying them without actually finding explicit formulas for the solutions. It turns out that equilibria and stability of equilibria, which is something we'll define in just a second, are really important tools for doing that, for understanding the behavior of solutions without actually finding the solutions themselves. So let's begin by finding what exactly is meant by stability. Now, suppose that we have a first-order system, y prime equals f of t and y, and that it has an equilibrium solution. So remember, an equilibrium solution is a constant that solves this differential equation. So that would be a constant you can plug in here and have it come out to 0 on the left and also be equal to 0 on the right-hand side. So given an equilibrium solution, what does it mean to say that a solution like this is stable? Well, what we mean is that if a solution starts close enough to the equilibrium, then it will stay close to the equilibrium for all time. Now, that's clearly not a rigorous mathematical definition. The actual definition is in terms of epsilons and deltas, and we're going to give it now. So we have two things that have to be close. We have to say that it stays close, that'll be measured by some number epsilon, and that it begins close, which will be measured by some other number delta, which is possibly smaller than epsilon. And the definition goes like this. It says that for all, should get my pen going. So for all epsilon greater than 0, there exists a delta greater than 0. So for no matter how small you want the solutions to stay, you can do it if you choose a starting distance that is small enough, that's the delta, such that for any solution y of t, if y of t0 minus ye, so the initial condition of our solution is close enough within delta units of the equilibrium, then the future values of your solution will also be close to the equilibrium. They'll be within epsilon units, and that's for all times that are greater than or equal to t0. All right, so formal definition, this should be familiar. This kind of thing should be familiar from the ideas of like continuity or differentiability. It's the same kind of definition. Now, then we have the ideal of instability. We say that y is unstable. Well, what does it mean? The stable means that solutions that start close enough will stay close. So the opposite of that would be that there's at least one solution that doesn't stay close, that starts close and moves away. So no matter how close you start them out, they will eventually get larger than your measure epsilon. Of course, the easiest way to define instability is this way. Unstable is the same as not stable, right? So it's the negation of the definition of stable. And so you might want to take a second to see can you negate that definition? Can you write the actual negation of it, right? Remember, that's a pretty, if you've been in Math 135, remember negation is not always a very straightforward process. So try it out. And then you can see if you match with what I got. So the negation of this is that there exists an epsilon greater than 0, such that for all delta greater than 0, there is a solution y of t such that the initial point is within delta units of the equilibrium, but a later point is not within epsilon units. So for some t0, for some t, Oh, that was a very large erasure. Let's see if I can put that back. For some t greater than or equal to t0. So that's negation. We're not going to use that formal version of this negation very often, but it is good to know that there is a solid mathematical definition of exactly what's meant by unstable. All right, and then finally we have a refinement of the idea of stability, a kind of souped up version, and it's called being asymptotically stable. So we say that an equilibrium YE is asymptotically stable if it is both stable and if all the solutions that begin near enough to YE approach it in the long run. So that's saying that the limit of the solutions is the equilibrium. That's not something that's guaranteed by the definition of stability. Things can just stay close without approaching. So this is a stronger version. So again, first of all, we need that YE is stable. So it has to do all the things that are in that first part of the definition. And in addition to that, there exists a delta greater than 0 such that if the initial condition is within delta units of the equilibrium, then the limit as t goes to infinity of y of t is equal to YE. Right? So things get closer. So there's three kinds of stability in a sense. There's really just stable and unstable, but then there's this stronger version called asymptotic stability. And so every equilibrium can be one of three things. It could be asymptotically stable, or it could be stable but not asymptotically stable, or it could be unstable, right? So three different possibilities: possibility 1, possibility 2, and possibility 3. All right, so let's try to take this definition out for a spin. So we have this two-dimensional autonomous linear system. And what we'd like to do is, first of all, show that the equilibrium, y equals 0, is the only equilibrium, and then analyze the stability of that equilibrium using the epsilon delta definition that we've just seen. So remember that if we do have an equilibrium YE, then it is a constant, which means that its derivative is 0. So if we plug that into the differential equation, since it's a solution, we get that -2, 1, 1, -2 times y will be equal to 0. So now all we have to do is multiply both sides by the inverse. This is an invertible matrix. So if we multiply both sides, by the inverse, which is 1/3 -2 minus 1 minus 1 minus 2, we get y on the left-hand side, identity matrix times y, equals, and on the right-hand side we get 0. So this is the only solution. 0 is the only equilibrium of this linear system. In fact, the origin is the only equilibrium of pretty much every linear system. As long as it's not a non-invertible matrix. Okay, so we've got this one equilibrium. Can we show that it is stable? Well, it begins with the solution in this case. Now, I've done the work ahead of time, and I know what the eigenvalues and eigenvectors of this matrix are. I know that I have an eigenvalue. So I have an eigenvalue, lambda equals -1, and it has an eigenvector 1, 1. And then I also have lambda equals -3, which has an eigenvector 1, -1. So solution will look like y of t is equal to C1, 1, 1, e to the minus t plus C2, 1, negative 1, e to the minus 3t. Now, we can get an idea from looking at this that this is probably going to converge to 0, that things are going to get smaller and smaller, which is a good thing for stability. So we're going to try to prove stability. We can think that because we do have e to the negative t and e to the minus 3t, both of those things are going to get smaller as t increases. In order to do this properly, though, we need to know, we need a measurement of how far the initial condition is from the equilibrium, and we need a measure of how far the later point of time, later value of the solution is from the equilibrium. So let's start with measuring the distance from y of 0 to ye. Now, y of 0 is C1, 1, 1, plus C2, 1 minus 1, and ye is 0, 0. So this is the vector C1 plus C2, C1 minus C2, and we want to take its magnitude. Now, if you recall, the magnitude of a vector is given by its Euclidean distance, so this would be C1 plus C2, the first component, squared, plus the second component, C1 minus C2, squared, and we take the square root of that. All right, so you multiply that out, get a little bit of cancellation, and what you'll find is that you have 2 C1 squared plus C2 squared. All right, we're just gonna save that up. That's equal to the magnitude of y, 0. Okay, now what about the magnitude of y of t minus ye? So later on, a different time, not time 0. Well, then it gets a little bit more involved. So first of all, ye is still 0, so this is going to be the magnitude of C1, 1, 1, e to the minus t, plus C2, 1 minus 1, e to the minus 3t. Magnitude. Okay, so what can we do with that? Well, we have to combine the rows together. We get that this is C1 e to the minus t plus C2 e to the minus 3t and C1 e to the minus t minus C2 e to the minus 3t. And so its Euclidean distance will be C1 e to the minus t plus C2 e to the minus 3t squared plus C1 e to the minus t minus C2 e to the minus 3t squared. That whole thing square rooted. So we've got a little bit of algebra to do here. We're going to have to multiply this out. C1 squared e to the minus 2t plus 2c1 c2 e to the minus 4t plus c2 squared e to the minus 6t plus c1 squared e to the minus 2t minus 2c1 c2 e to the minus 4t plus c2 squared e to the minus 6t. Now you might be getting the impression at this point that this is wearisome and we'd really rather not be doing this. That is absolutely true. And we are doing it so that we can see how it works, but then we're also doing it in order to get an idea of why we want to have alternate approaches, why we want to have a roundabout way of figuring out the stability of an equilibrium, a little more computational way that doesn't require this kind of heavy lifting. Okay, so where are we at now? Well, we've combined a bunch of stuff together. We've still got a little bit more to do. We have 2c1 e to the minus 2t plus 2c2 e to the minus 6t. So this has gotten much simpler. That's nice. And we can factor out, in this case, we can factor out a 2, c1 squared, sorry, those are supposed to be squared in there, plus c2 squared, missed something there, e to the minus 4t times e to the minus 2t. So we just factored out the 2 from the front and the e to the minus 2t from the back. And now what we're going to notice is that this term, the e to the minus 4t, is less than 1, so that this whole thing here is less than or equal to the square root of 2 times c1 squared plus c2 squared, e to the minus 2t, which is the square root of 2c1 squared plus c2 squared times e to the minus t. And you might recall this thing here is y of 0, e to the minus t. So what can we tell from this? Well, we can tell that, in fact, this is always going to be less than or equal to y of 0. Yeah. So the idea here is that if our initial condition is sufficiently small, then the later values of y of t are actually going to continue to be smaller. They're going to get closer and closer to the equilibrium E as time goes on, right? They're always going to be less than the initial starting point. So if you start within epsilon or within delta units, you'll actually stay within delta units. So if you pick an epsilon, you can always just let delta be equal to, or let delta equal any number less than or equal to epsilon, and the definition works. So in this case, 0 is stable. Now, as I've said, this is long and wearisome and no fun. So we're gonna develop now a theorem that will help us do this much more quickly, and hopefully it'll be appreciated now that we've seen how bad it can be. So this is theorem 6.3. It says, so okay, let's let A be a real invertible 2 by 2 matrix. Then the autonomous linear system, y prime equals ay, so just like the one that we just saw, has a unique equilibrium, y equals 0. We know why that is now. This equilibrium point is asymptotically stable if what? What has to be true? Well, it turns out that all we have to do is look at the eigenvalues of the matrix A. So our condition is that both eigenvalues of A are real and negative, or are complex with negative real part. So we just need negativity, basically. And so for the real negative ones, we can see why this would be. The solution will have e to the lambda t, and if lambda is negative, then that part is going to go to 0. So things are going to converge to 0. And the same thing goes with complex with negative real part. We're always going to be able to pull out e to the minus alpha t, e to the alpha t, the real part, times t, and that exponential will go to 0. Now, this system will be stable, but not asymptotically stable, if the eigenvalues of A are purely imaginary. All right, so what does that mean? Just as a recall, that means complex with real part 0. So that would be something like plus or minus 2i would be an example of purely imaginary eigenvalues. And then finally, the equilibrium 0 is unstable if any eigenvalue is real and positive. So it doesn't take both, just one of them being real and positive, or complex with positive real part. All right, and here we're relying on the fact that eigenvalues of real matrices are complex conjugates. If they're complex, they come in conjugate pairs, which means that their real parts are always the same. So it's not possible to have a negative real part and a positive real part in the same set of eigenvalues. So these are our conditions. We're just looking at the eigenvalues and deciding, are they both negative, or do they both have negative real part? If so, then it's asymptotically stable. If not, then it will be unstable if one of them has a positive real part, and it will be stable but not asymptotically stable if the real part of both of them is 0. All right, let's see how easy this is to use. Let's go back to our previous example. We have our linear system. How do we analyze the equilibrium using theorem 6.3? Well, we know from before that the eigenvalues are -1 and -3. And that means that it will be asymptotically stable. Why? Because these are both negative. That's it. That's all it takes to prove asymptotic stability. All right, let's try another. Now let's look at this system. Same kind of deal. We have the matrix 1, 1, -1, 1. In order to figure out the stability, we just have to find the eigenvalues. So we're going to do 0 equals the determinant of 1 minus lambda, 1 minus 1, 1 minus lambda. So that's 1 minus lambda squared plus 1 is lambda squared minus 2 lambda plus 2. Okay, so now all we have to do is figure out what the eigenvalues are and solve this equation, basically. So we're going to use the quadratic equation. Lambda 1 and 2 are equal to -b, so 2 plus or minus the square root of b squared minus 4ac over 2a. And that gets us 1 plus or minus I. So these are complex. It's a complex conjugate pair. And the real part is greater than 0. So what does that mean? That means that this one is unstable. Okay, so the thing that I left out here is that I did say, both of these problems do say, hey, let's sketch the phase plane of the solutions. So let's go back to the previous example and do that. Sorry, I skipped it over. So in this example, remember we had these two eigenvalues and we had the eigenvectors that went with them, 1, 1, and 1, minus 1. So we can put together a phase plane by thinking about these directions. The eigenvalue directions have solutions that go out in them. So we'll have solutions along the vector 1, 1, and along the vector 1, -1. And so those are going to be solutions. It's asymptotically stable, so everything is going to move inward along this. And every other solution is made up of some combination of these things. So it turns out that this is going to have, all of the solutions are going to converge toward the origin. That was not a very good one. I have to clean that up a little bit. So let's see if we can fix that. So solutions will head in like this. So all the solutions go toward the origin. In fact, you could draw them reaching the origin if you so desired. All right. So that's what it looks like for things to be, one of the ways that things can be asymptotically stable. Over here for this one, the picture is a little bit different. Trying to do my things right here. So we get unstable. And what does that phase plane look like? Well, these are going to be complex. So we're going to have kind of a rotation, and it's going to be moving outward. So what we'd expect here is we would have solutions that rotate, but they rotate in an outward direction. Right? So solutions will spiral out. This kind of rotational action is always associated with complex eigenvalues, and either going in or out is associated with real eigenvalues of the same sign. And we'll deal with real eigenvalues of opposite